In this lesson, we're going to learn how to simplify radical expressions. Our central question, explain how to simplify a radical expression. And I know that's not a question, it's a statement, but we need to be able to describe how to do this once we're finished. So take a minute, set up your notebook, and begin the video when you are ready. The first thing that I put down for you is I want you to notice these kind of criteria for when something is in simplest radical form. Simplest radical form means there are no perfect squares other than one in the radicand. There are no fractions under the radical sign, and there are no radicals in the denominator. For today's lesson, we're mainly going to be focusing on step 1 because we shouldn't have any fractions or any kind of fractions that would apply to rule 2 or 3, but we need to keep that in mind. Let's first write down a definition for a radical expression. It's very, very simple. A radical expression is simply an expression with a radical sign. And today we're going to just look at very basic ones, but in the future days we will be looking at expressions that have adding and subtracting, multiplying, dividing, and so forth. So we're not going to just be looking at the basic ones today or in the future. Okay, here's an example. The square root of 9. Some vocabulary I want you to note is we know that this is a square root sign, but you'll remember previously we may have talked about that this is also called a radical sign because we can have other roots besides square roots. This number underneath the radical sign is what we call a radicand. Okay, a radicand is the number underneath the radical sign. And this whole thing makes up a radical. Pretty cool, huh? Radical. I hope we all know, too, that the square root of 9 is 3, because 3 times 3 is 9. So remember, we're looking for pairs of numbers, perfect squares, pairs of variables, and so forth. So let's talk about how we're going to simplify this expression. We're going to simplify this expression by writing the radicand. So we're going to write the radicand as a product with perfect squares. So as we look at these numbers, as we look at our radicands, we need to think about what is a perfect square that I can multiply by something else to get that number. Okay, so for example, 32. We know 4 times 8 is 32. Hopefully we also know that 2 times 16 is 32. Both 4 and 16 are perfect squares, but we want to pick the larger perfect square because if we didn't, then we wouldn't be in simplest radical form. So we're going to see that 32 can factor, because that's what we're doing, 2 and 16 are factors of 32. 32 factors to 2 times 16. Well, this makes it really easy to take the square root. We can separate these and think of these as individuals now. 16 is a perfect square. The square root of 16 is 4, but lonely old 2, it isn't a perfect square, so it has to stay under the radical sign. Okay, another example. Square root of 48. Again, I want to think of perfect squares. So, of course, 1 is a perfect square. That's not going to help us. 4 is a perfect square. That would be 4 times 12. That works for 48. 9 is a perfect square. It doesn't go into 48. Let's see. Then we have 16 is a perfect square. So that also, in this case, the 16 is going to work again for us. We could pick 4. But then we would have to realize that 12 has some perfect squares as part of its product, so we wouldn't be done. So the square root of 48, a way to factor it would be 3 times 16. And so we know the square root of 16 is 4. So the square root of 48 is 4 the square root of 3. And so this would be an example of 2 being written in simplest radical form. Okay, 2 more examples down at the bottom. We're throwing in some variables. And we have talked previously about when a variable is a perfect square. Remember, our exponent must be even. But that doesn't mean if the exponent is not even that we couldn't factor it to have an even exponent. So we want to look for pairs of the variable. So let me show you what I mean, because that sounds kind of weird. We have x cubed. Hopefully, if looking at x cubed, you realize that I could break that apart into x squared times x. X squared times x still means x to the third, right? And then 9, I don't need to break that apart into anything because 9 is already a perfect square. So now I've set apart all my perfect squares. The square root of 9 is 3. The square root of x squared is x. And so the only thing left under our radical sign is our lonely old x. It doesn't have a partner. It doesn't have a pair or perfect square to bring it out of the radical sign. Okay, let's look at the next example. 28, thinking about our perfect squares, would factor to 4 times 7. We have x cubed, so x squared times x. And I didn't make my radical sign big enough. And then y cubed, y squared times y. So let's look at my perfect squares. I have 4. The square root of 4 is 2. The 7 is going to stay underneath the radical sign. I have x squared. The square root of x squared is x. I have a lonely old x with no partner. I have the square root of y squared, which is y. And then I have a lonely old y left over. So here would be my simplest form. This can be a really difficult topic, so I don't want you to stress out if you have a lot of questions. I would like you to try these 2 problems on your own so that we have a starting point for a discussion in class. So I want you to try to simplify the square root of 45. And I want you to try to simplify the square root of 150 x to the 4th, y to the 5th.